Hi, I'm Raya Weimer, and this is my reassessment for organic reactions. The first organic reaction I'm going to be talking about is addition reactions. This is when two atom molecules, such as hydrogen, are added across a double and triple bond. This is when you're putting something into a molecule without taking any atoms out. And this reaction involves alkenes and alkynes. The examples I have provided will explain more. So if you have an alkene plus H2, it will turn into an alkane. This is going from a double bond to a single bond. You also have alkyne plus H2 and turning into alkene, going from a triple bond to a double bond. And if you have an alkene plus 2H2, it will turn into a single bond. Here in this drawing example, you can see that when you add two hydrogens to a double bonding carbon, it breaks the double bond and turns it into a single bond. It goes from unsaturated to saturated, or in other words, not full to full. The next reaction we have is a substitution reaction. This is when an atom replaces another atom that is already present in the molecule. It involves alkanes and halogens. It is a very slow reaction and it requires ultraviolet light, and that acts as your catalyst, which speeds up the reaction. In the example below, it shows propane plus 2 fluorine. Here, the fluorine will replace one of the hydrogens in the propane and turn into 1 fluoropropane plus hydrogen fluoride as a byproduct. The next reaction is elimination. This is when a molecule is removed from the organic molecule across two carbons, thus creating a double bond. It's the reverse of the addition reaction. It creates unsaturated hydrocarbons, and unsaturated means not a full molecule. This elimination reaction needs an acid catalyst, and you can use H2SO4. This elimination reaction comes in two different types: dehydration, which removes water from the compound, and dehydrohalogenation, which removes water and a halide ion. The first type of elimination reaction is dehydration. And in order to tell if you have an elimination-dehydration reaction, you can look and see if your reactant is an alcohol. And to do so, you'll look for an OH. An OH determines if it is an alcohol or not. So in our first reaction, you can find the OH, and you will be removing that as well as a hydrogen. And dehydration is the removal of water from a compound. So you'll need to have an oxygen in order to make water, hence the alcohol. The second type of an elimination reaction is dehalogenation. Just like dehydration, you'll need to have an alcohol as your reactant. But as well as water, you'll need to remove a halide ion. So here you have a bromide and a hydrogen as well as an OH. So you'll be removing that to get H2O plus bromide. Next is polymers. These are long continuing chains containing simple repeating units, which are known as monomers. In order to tell if you have a polymer, there'll be square brackets around your compound, or you can see that is repeating like in the photo. The next reactions are combustion reactions. Combustion reactions are when hydrocarbons or alcohols react with oxygen, which then produces carbon dioxide and water vapor. In the example below, it shows complete combustion. Complete combustion occurs when there is enough oxygen to completely use up all the reactants. In some cases, incomplete combustion occurs, and this is when there is not enough oxygen, resulting in the production of smoke. In real life, combustion reactions are the reactions that allow fuels to produce heat. The next organic reaction is esterification reactions. It is like elimination reactions as it involves the removal of water. When you remove water from alcohol and carboxylic acid, you will make an ester, thus esterification reactions. The next topic is fractionation. Fractionation is a separation process where a certain quantity of a mixture is divided into a number of fractions. Fractionation makes it possible to isolate components in a mixture. In order to explain fractional distillation towers, I'm going to use real-life examples. So the first stage of petroleum refining is fractional distillation, or fractionation, of which we just talked about. Most components of crude oil are vaporized and then condensed at different heights in the fractionation towers, depending on their boiling points. The crude oil is thus separated into fractions of similar boiling points. So if we look at the slide in the photo that I provided, it shows the distillation tower. This tower relies on different boiling points of various hydrocarbons found in crude oil. Here, at the top of the tower, the lowest boiling points condense at the top, where the temperature is the coolest, and the highest boiling points condense at the bottom, where the temperature is the hottest. Continuing talking about boiling points, when you look at an organic compound, it can tell you if there's going to be an increase in boiling point or a decrease. So, if you have an increase in carbons, the boiling point will increase. However, if you have branches on your organic compound, it will decrease the boiling point. Hydrogen bonding also increases the boiling points, as well as if you have an alcohol or carboxylic acid. As we continue to talk about the idea of fractions and fractionation, we move into this process called cracking. Cracking takes compounds with larger number of carbons and breaks them down to compounds with smaller number of carbons. Next is catalytic cracking, and it is an endothermic reaction. It uses an acid catalyst to crack and produce lighter and more valuable products. Catalytic reforming is the reverse of cracking. It converts straight-chain carbons into branch alkanes, aromatics, and more, and it involves the removal of hydrogen atoms. The last type of cracking is hydrocracking. Hydrocracking is hydrogenation combined with catalytic cracking. Hydrocracking is the process in which the components of gas oil fractions are partially or completely converted into lighter molecules under the influence of H2 in the presence of a catalyst. The last thing I'm going to touch on is London dispersion. In organic chemistry, the compounds undergo a force called London dispersion. This is where electrons are shared equally between atoms. Hydrocarbons undergo London dispersion as they are nonpolar. However, London dispersion is weak, and the more electrons present, the stronger the force. As carbon chains increase, so does your London dispersion. London dispersion is also strong when carbons are in a straight line. Now here we come to the end of my presentation. I hope you enjoyed. Bye!